Hello, and welcome to the beginning of this mini course on Heegaard splittings and Dehn surgery. Today, we're just going to talk about the basic definitions of Heegaard splittings. And I figured that where we will start is defining what a handle body is. I'm sure most of you know this already. So one handle is just a disk crossing interval which we can attach to a three-manifold via an attachment map, which is defined right here, from the endpoints of the interval in the disk to the boundary of the manifold that we want to attach it to. All right. So here's an example. Say you have your manifold M, and you have your one handle. There's a nice one handle. And this is the region that we want to attach. Let's say we want to attach it here. And the map F just sort of glues this onto those regions. All right, so from this, we can define a handle body. And here we're going to be working in 3 dimensions. There are higher dimensional analogs of all these definitions. A handle body of a certain genus is a 3-manifold attained by attaching G1 handles to a 3-ball. The homomorphism type depends only on the genus, and the boundary of a genus G handle body is a closed ornamental surface of that same genus. And here's an example of a genus 3 handle body. All right. So now we get to the main definition for today, which is, suppose we have 2 genus G handle bodies, H and H prime. They have homeomorphic boundaries. So we pick some homeomorphism F, which is right here, between the boundaries. And when using this homeomorphism F, we can glue their boundaries together. And when we do, we get the 3-manifold. And this gluing together, which we use this notation here of H union H prime with the map F. Sometimes the map F would be suppressed when the map is sort of obvious in the picture. We call this a Heegaard splitting of the 3-manifold M, and then it's the Heegaard splitting of genus G, which is the genus of the handle bodies. Also, we have take those off. We also call the surface, which we're gluing these handle bodies together through. We often call this the Heegaard surface of a manifold. So if there's a homeomorphism of our manifold M, which takes one Heegaard splitting to the other, then we just consider those equivalent. They're the same Heegaard splitting as far as we're concerned. All right, let's go ahead and start doing some examples. So first example that we're going to start with, of course, is S3. It's always a good example to start with. And so let's pretend like this little white space here is S3, and we can draw a 2-sphere inside of S3. And clearly this 2-sphere bounds a 3-ball inside. This is a genus 0 handle body. But it also bounds a 3-ball on the outside. And of course, we have obvious gluing here. We just glue these together through the boundary. And we get that S3. S3 is a gluing together of 3 disks. Here, I guess this map F is technically this gluing that's sort of here in the picture. But it turns out in this example, it doesn't actually matter what F is. You'll always get a 3 sphere, which we're going to talk about why that is a little bit later. So this is a genus 0 Heegaard splitting. Yeah, of S3. So let's stick with S3. And this time, we're going to start with the torus. Nice standard embedded torus like this. Of course, this torus bounds a genus 1 handle body, which is S1 cross G2. Then also, which is a little bit harder to see, it bounds this GS1 handle body on the outside like this, that kind of goes through the hole and comes out the side. And it might be kind of hard to see. One way you can see this is if I took a cross section of this torus. So this is our cross section of H here. Then you can see that inside the complement, we have a disk that you can kind of glue in right here. That's the same disk that's right in here. And I get a whole S1's worth of disk, where this one right here goes through the point at infinity. Then we sort of start coming back over on the other side. So it looks like a magnetic field. You can see we kind of get a whole S1's worth of disk. Right. So it actually is a solid torus. All right, so here's a genus 1 Heegaard splitting of S3. Now, of course, these examples might seem a little easy because we sort of started with the manifold. And we can easily visualize S3. Let's do another example. Let's now start with some handles. So let's say that our 2 handles are solid tori. And I'll just draw them side by side like this. So we're starting with the handles. We're not starting inside of our manifold anymore. And let's glue their boundaries together along an identity map. And by identity map, what I mean is that if I, think about the picture here, F just takes it to like the same picture over here, right? All right. So what manifold do we get here? Well, if I take this curve on the boundary which bounds a disk, this curve gets mapped by F to another curve on this other handle body, which also bounds a disk, which means together, let's call this D1 and this D2, which means together, we get a 2-sphere. And again, as we kind of go around this manifold, we get a whole S1 worth of these 2 spheres. So we get that if we glue these together along this map F that we specified here, this is F, get S1 cross S2. All right, so now we've already seen two genus 1 Heegaard splittings. They gives you a different manifold depending on how you glue the boundaries together. So that's the basic idea of a Heegaard splitting. Any questions so far? All right. So let's talk about our first theorem. So notation I'm going to use, since I'm going pretty closely by the book, and you might want to look these things up later, I'm going to have my numbering here. But then I also will give you a reference of where the theorem is in the book in case you want to look it up. So this is theorem 1.1 in the book. So every closed orientable 3 manifold has a Heegaard splitting. So why is this true? So first, we're going to take a closed orientable 3 manifold. And we're going to use this one fact, which is not trivial, which is that M has a finite triangulation. T. This was first proved by it's actually pronounced Moyse. I always forget. Anyway, it was first proved in 51 by Moyse. There's some other proofs after that. All right, so once we have a triangulation, I'm going to use this notation UT1. And this just means we're going to thicken the one skeleton of T. To find that. And then I'll say that UT1, this is, let's go up a little bit. This is a handle body. And it turns out that this, however way you want to see this, you can look at the dual triangulation to T. Is one way you can see this. But if I look at the complement, which I'll denote this way, and here we're going to actually just take the closure of everything when we say complement, just to make sure that everything is nice and compact. This is also a handle body. And they have the same genus. And of course, M is just the thing you get when you glue these things together. So there's our Heegaard splitting. All right, so now that we know that every 3 manifold, well, every 3 manifold, but we're really talking about closed orientable manifolds, has a Heegaard splitting. I'm going to go ahead and define the Heegaard genus. So the Heegaard genus of a manifold just means the minimal genus of a Heegaard splitting of M that we can find. So for example, S3 has Hegeogenesis 0, as we've already seen. It turns out this is the only manifold of Hegeogenesis 0. Which means that S1 cross S2 has Hegeogenesis 1, as we've already demonstrated. All right, so typically a manifold is going to have lots and lots and lots of Heger splittings. And we know sometimes they can be equivalent, but of course to be equivalent, you know, they have to be, they have to have the same genus, right? But you can also have higher genus Heger splittings of the same manifold. Like for S3, we already seen one that was genus 0 and genus 1, and you can make these arbitrarily high. So we're going to develop a way to relate two Heger splittings of different genus. And the way we do that is this process called stabilization. So the idea is, suppose that we have a manifold and we have some Heger splitting of genus G, which you can see here. So the goal of this section is to construct a genus G plus 1 Heger splitting. This is how we're going to do that. So we're going to start by attaching an unknotted one handle. And when we say unknotted, what does this mean? Let's give this label, B to H G. And by unknotted, we just mean that that it bounds a disk. I just say B union the first handle body bounds a disk, which we're going to call D. So let's draw a picture here. So let's say the HG looks like this. And then we can glue on, I think I'm gonna do it this way. So there's an attached one handle. This is B. If we had this picture, we could see that there's a nice disk in here, like that it bounds. All right. Once we have that,
sorry, John.
Yes.
When you say bounds a disk, that disk is living in the ambient free manifold?
Yes, it's living in M. So we already have a manifold M in the Heger splitting.
Yeah.
So it bounds a disk in M.
So this handle that you've glued on is a subset. Is a subset of the manifold, or?
It is a subset of the manifold. Yeah.
Okay. Okay. All right. Thanks.
So now we're going to thicken D to get C, and all we're doing is just thicken it. You know, I'm not going to even really draw it really. You're just making this like a little bit thicker. Just, you know, and what you notice here is that if I take HG and then add on this one handle B, and then add on this I'll try to label this like this, C. And then add on C. Well, this is just Hg with the 3-ball added on, right? Which is isotopic to just Hg that we had in the beginning. And the reason why this is important is this means that if I look at Hg prime, which would have been the complement of our original handle body. So if I look at Hg prime and I remove this, and let's say I take the closure of it just to be sure. This must be isotopic to just Hg prime. And in particular, this means that this is a handle body of genus G. All right. Are we all good so far? So now you can kind of see how we're going to build this Heegaard splitting with one more genus, right? I call this Hg plus 1. Well, we're just going to take our original genus G handle body and just glue on this one handle B. And Hg plus 1 prime, we're going to take this guy here, which was, what was that? Hg prime minus B union C, take the closure of it, and then we're going to glue on this C part, glue C back in. So these are both handle bodies of genus G plus 1. And when we glue them together, we should get the exact same manifold we started with. So this entire process is called stabilizing, right? This Heegaard splitting is a stabilization of our original Heegaard splitting. And we say that two Heegaard splittings are stably equivalent if they can be made equivalent by a finite number of stabilizations. All right. So the rest of this talk is going to be focusing on this theorem, which says that any two Heegaard splittings of a 3-manifold M are stably equivalent, right? So given two Heegaard splittings, I can't stabilize one to the other, but I can stabilize each of them some number of times until I get the same, until I get an equivalent Heegaard splitting. That's the idea. So why is this true? This is going to follow from two lemmas. The first is that if I take any two Heegaard splittings of a manifold M, and if these Heegaard splittings were given by triangulations, I say, then there are stably equivalent. And the proof of that, I'm just going to leave as an exercise. So intuitively, if you think about how we built the two triangulations, how we built the Heegaard splitting from a triangulation, and you know that two triangulations, you can sort of have a common refinement. You can just fill in the details of that argument of how you can sort of build to that common refinement using just this normal stabilizing move that we did above. But I'll let you guys think about that one. And we're going to focus on this lemma, which says that any Heegaard splitting of M stabilizes to one that's given by a triangulation. All right, and if you put these two lemmas together, then we get the theorem. All right, so why is this last one true? So we're going to start with Heegaard splitting of a three manifold M. And then we're going to find a couple of things. We're going to find triangulations. I'm going to call this tau and tau prime of H and H prime, respectively. Which satisfy the following. So the first thing that we want here is that we want for the thickening of the one skeleton of, ooh, this is bad notation. The thickening of the one skeleton of tau, we want to say this can be attained from a graph, from a graph gamma. Well, I'll find this later. By adding unknotted one handles. And here, gamma is, I forgot what word they used in the book. I think they call it an axis, but it's basically, I don't use the word they use, be consistent. Yeah, that's it, axiograph. Of H. All right, so what does that mean? So that just means that, H is some handle body, right? And gamma is just some graph like this. So the deformation retracts to gamma. All right, so that's the first thing we want. The second thing we want is for if we thicken the triangulation for H prime, I want this to be able to be obtained from, I'm not going to use this notation the boundary of tau prime. And all this means is just take the triangulation and restrict it to the boundary, you get some triangulation of the boundary, right? So you take that triangulation of the boundary, you thicken it, and you should be able to start from there and get to the triangulation of the entire handle body for H prime. Similarly by adding unknotted one handles.
Jonathan, can you describe how in that picture, the H is obtained by adding unknotted one handles to that green graph?
We're going to get there in a minute.
Oh, okay.
I have not demonstrated why that can happen yet, because it makes you feel better. All right, and the last thing that we need is that if I apply, I guess I didn't label the gluing map, but the gluing map should be F. If I look at the image of, the triangulation of the boundary of the first one, hopefully I get the triangulation of the boundary of the second one. So we can glue these triangulations together in the end. That's the goal. So what should I do first? I think first I'm going to finish, if you have these things, why it's true, and then we'll talk about how you can actually get triangulations that do this. So if this were true, then what you say is that, okay, well, if I started with a neighborhood of gamma, I can, add these one handles that are unknotted. And get the triangulation of H. And then once I do that, I can add more one handles. And get a neighborhood of the triangulation that you get by gluing these two together, which we can do because the boundaries triangulations match. All right, I'm going to call this T. All right. And then we say, oh, but this guy right here, this guy, well, this was just isotopic to the original handle body H, because it's just the axial graph. The code deformation retracts them to it. And therefore, we can just write this line that this Heegaard splitting is equivalent. It's not the exact same, so I'll write this. It's equivalent to a Heegaard splitting given by taking a neighborhood of gamma and its complement. And then we can stabilize. You get to a Heegaard splitting given by I think the neighborhood of, well, the one skeleton of the triangulation, I should say. These all should be one skeletons technically. Of the triangulation in its complement. And that's what would complete the proof if we knew we can find a triangulation that did these things above. And since we have a little bit of time left, we can talk about how we can find the triangulations that actually do this. It's actually not super difficult. In the book, Nikolai basically just says, like, you know, just do the first thing that comes to your mind is probably going to work. And he's kind of right. So here's an example. I'm going to draw a genus 2 handle body. I'm going to draw it all blocky-like, though, so we can make it nice and... And then you can just sort of demonstrate some way that you can triangulate this, where you always get this as sort of, we can always sort of satisfy this condition above, right? You know, so here's just one example. There's plenty. I could always just do this thing on top. And then I guess they should be triangles, so we can just add some things in here like this if you want it. And then we can just sort of do the product of this. So we get the same thing on the bottom, and we get, you know, all of the necessary all necessary edges all around this thing. And if you really want to be official, so this technically is not triangulation. You would go ahead and take each of these prisms that we've broken up this handle body into, you know, and just do whatever your favorite way of dividing this into, you know, three tetrahedra. So we get something like this. And here you can clearly see that, you know, you got something like this right here. It's like gamma right there, right? And you can do this for arbitrary genus. You can do the same pattern arbitrarily high, okay? So this actually is not quite enough. So I say this we do for H. To really make this work, we should actually do this for H prime also. I was going to do the thing on top like this. You know, I do like that. Fill it out the exact same way you do above, right? I won't complete it. So we can do this for both H and H prime. And the whole point here is that, so it's very clear here that the theme that I created here, this will satisfy, this condition here. Not high enough. This will satisfy this condition here, and it will satisfy this condition here, right? You just got to make sure it satisfies this gluing condition here. And this I will not do in detail, but basically, you know, I do get some triangulation of the boundary here. So I then can just look at the image of both of these triangulations that we have on our surface. So if I look at the orange on H prime, I'm going to get some other triangulation that does whatever. I don't know exactly, right? You know, that's just some other thing. Same thing up here, right? And then you just sort of do whatever appropriate refinement you need to like make this into a proper triangulation. And that's how you get your, and that's how you define your tau and tau prime. And it'll satisfy all the conditions.
Is it obvious it's going to be like transverse like that? Or that you can make it transverse?
Yeah, you can make it transverse because the way I sort of, like, I know that each handle body is like homeomorphic to this blocky thing I did, but this is kind of arbitrary, right? I can always sort of move these, you know, I can always move the triangulation around to like make it transverse if I really needed to.
I think I still don't understand what it means to add one handles to this graph.
All right, so let's just take one triangle that we might end up at the end here, end up with at the end. So let's take, actually let's do it this way. Let's say this part right here is gamma. And let's say this is part of some triangle like this, right? And then maybe do other stuff like this. So if I thicken this, so this, you know, has thickness now. If I wanted to really add on to this guy, I could add on this guy right here. And if I set this up right, there should be a disk here, which is just one of the two simplices from this triangulation. Just sitting in here. And so I've added on a one handle, which will bound the disk. And then maybe perhaps it looks like this. And so then maybe I'll just take another edge and then I add on another one handle like this. So it looks like this. And the whole point here is that when I'm adding on these triangles, I add it on in a way in which these one simplices always bound two simplices. You know, something like this. That's what you want to make sure you can do. It could be you just need to add in one edge, and there's a simplex here. That's the idea. But the whole point is that you want to be able to always have a two simplice whenever you're adding in these one simplices, right? Does that make more sense?
Yes.
All right, any other questions? That was the end of that level.